Hi everybody and welcome to another video. Today we're going to cover high resistance grounds. This can be high resistant grounds in medium voltage 4160 or low voltage 480 systems. So the main reason why we install high resistant ground is to limit the fault current. Now that's reason number one, and when we limit the fault current, it contributes to a host of different things happening. Number one, it reduces the arc flash. Two, it prevents equipment damage because you don't have that surge of current running through the equipment. And three, it limits the downtime. Now imagine you're a cement crusher or you're a facility with heavy motors, large equipment. That fault current for a ground fault that does not have a high resistant ground in place, it can actually burn up the core of those motors, and that's pretty costly. If you're a data center, it's going to cost you a lot of time to be down. I mean, a couple of minutes of downtime on your servers can cost you tens of thousands of dollars, if not more. So we're going to go over a couple examples of high resistant ground and how it kind of limits the current, and how you can check and make sure that your high resistant ground in your system is up to par. Okay, so here's a Y system. It is ungrounded. You have phase A, B, and C, and here you have the neutral coming out, and it's grounded right there. Now, suppose you had a ground fault happen on, say, phase B. What would that look like? So you would have this go to ground right here, and then you would have the ground current run through here and back up through this transformer here. Now, the resistance that's in this ground right here, the path that the current takes, the resistance that it faces, let's call it Z ground. Now, what is the current going to be? What's the max the current can be? So IG, effectively, without going into sequence components, just simply it's going to be the voltage, the line to neutral voltage, divided by ZG right here. Okay, and that you can imagine that ZG is going to be pretty tiny if you have a solidly grounded fault right here with nothing in between. Now, the high resistance ground is designed to limit this current. With the high resistance ground, you're actually going to have a value here of a couple ohms, and that's going to limit some of the ground fault. So let's take a look at a system that has that. Okay, so here's a Y transformer again, except now we have a high resistance ground, which is right here. Here's the resistor. So now say we have that same fault. So what's going to happen is you're going to have the fault right here. It's going to go to ground, and the ground fault is going to flow this way. Now what's going to happen is when it comes back up through the transformer, it's going to be limited by this resistance right here. So effectively, you're going to have a formula of IG is now going to equal the same thing, except now you have a real resistance value, and this is going to be in a couple of ohms. So say, for example, that you wanted your ground fault to be limited to 600 amps because that's the most that your motor could take without burning up. So let's see how that would look. The formula for that would be, so we have IG is, we want to limit it to 600 amps. So your resistance, your high resistance ground is going to be equal to, let's say this is a, and you know our voltage here, let's say this is a 2400 volt system. So it's going to be 2400 volts divided by 600. And then we're going to have something, what's that? That's 4 ohms. So we're going to have 4 ohms here for a 2400. That's voltage, line to neutral. So that makes it actually a 4160 system. 4160. Okay. So for a 4160 system, you're going to have your voltage line to neutral 24,000 volts divided by 600 amps, because that's how much you want to limit it to. Is it going to be equal to 4 ohms? So if this is equal to 4, if this resistance was 4 ohms right here, you would be able to limit your ground fault current to 600 amps. Now, let's go over how to check, make sure this resistance is in good working condition. What you're going to want to do is you're going to want to disconnect the ground from the neutral here that comes out of the transformer, and you're going to want to do an insulation resistance check between the ground and the neutral. And ideally, you should be an open circuit, so you should read a couple giga-ohms. And if you do find that it's a short circuit or that the path is closed, you're going to want to check your loads and make sure that nothing is connected to ground. And if you're working on a main system, a lot of times these feeders run a distance, and they may be tied into another system or something else that is grounded. And if it should be grounded, that's fine. If it shouldn't, you need to verify that that fault current isn't going to run back on your grounding system and defeat the purpose of this high resistance ground. Next thing is, just with a meter, you can check the resistance of the resistor here. Just make sure that it matches the nameplate, and then you should be good to go. If you guys have any questions, comments, feel free to leave it below. Thanks.